This is Mallikarjun, working as assistant professor in the department of Flickr IARE. Today we are going to discuss about the steady state analysis. So we are trying to calculate the steady state analysis output for the different combinational circuits. Different combinational circuits, either the elements are connected in series or the elements are connected in parallel. And in the today's class, we are going to discuss about the steady state analysis of a series RL circuit. That is, I am trying to connect the resistor and also an inductor in a series, and I am trying to analyze the response of it. What is the steady state response or output that has been obtained in the for a series RL circuit. So series RL circuit, in general, the representation of series RL circuit can be represented like this. So I am taking a circuit which consists of a resistance R and an inductance L, which are connected with respect to an AC voltage source. And let me name that the AC voltage source is given as V equal to Vm into sin omega t. As we know that as both the elements are connected in series, the current flowing through both the elements will be same. Whatever it may be, if the n number of elements are connected in series, the current flowing through the first element and the current that is flowing in the last element will be same in case of a series circuits. Let me say that the voltage drop across the resistor is considered as some VR, and the voltage drop across the inductor is considered as VL. Voltage drop across the inductor is considered as VL, and let V be the supply voltage, where the voltage here considered as an AC voltage source. AC voltage source. AC voltage source. So this is the circuit for which we are trying to analyze the behavior of this particular circuit and trying to calculate the steady state response of it. Steady state response of it. So RL series circuit, I am naming the resistance as R and I am naming the value of inductor as L, and the supply voltage is given as V equal to Vm into sin omega t. The current flowing through the circuit is given as I. Voltage across the resistor is VR and voltage across the inductor is VL. Voltage across the inductor is VL. So the IR, the current flowing through the resistor IR and the current flowing through the inductor IL will be same. These both are equal to I, the current that is flowing in the circuit, because the resistance and inductors, the resistor and inductor here are connected in series. In a series connected circuit, the current flowing in the first element and also the current that is coming out of the last element will be same. So I can clearly state that I equal to IR equal to IL. I equal to IR equal to IL, where IR is the current flowing through the resistor and IL is the current flowing through the inductor. Both the currents are equal to the current that is flowing into the circuit, as both the elements are connected in series. As both the elements are connected in series. Connected in series. Now we are trying to draw the phasor diagram representation of a series RL circuit. Phasor diagram representation of a series RL circuit. So in order to draw that particular phasor diagram, we need to follow certain steps. We need to follow certain algorithm or a step-by-step procedure in order to draw this particular phasor diagram. So as it is a series circuit, as the current flowing in this particular element at the first point and the last point is same, let me take the current vector as a reference. Let me take the current vector as a reference. Let me say that I have taken current as a reference. And I know that the voltage drop across the resistor is considered as what? VR, and the voltage drop across the inductor is considered as VL, where VR is considered as what? I into R, the product of resistance and also the value of current that flowing in that particular element. That is nothing but I. So this is the formula of what we got from the Ohm's law. Ohm's law. Now if you want to calculate the value of this particular voltage, that is VL, voltage across the inductor, the general formula to calculate the value of voltage across the inductor is given as I into XL. That is current flowing through the inductor I, and XL is nothing but what? Inductive reactance, where XL can also be written as 2 pi FL. 2 pi FL. So as we know that the property of a resistor is, so depending upon the properties of the resistor and depending upon the property of an inductor, we are trying to draw the phasor diagram by current as a reference here. So what are the steps we need to follow in order to draw the phasor diagram of series RL circuit? First, we need to take the reference position. Then we need to know the properties of elements which are connected in that particular circuit. So in our circuit, we have resistor and inductor. We need to know the property of a resistor, whether the current is in phase or lagging or leading. In the similar fashion, we need to know the property of an inductor, whether current is in phase or else whether the current is lagging the value of voltage or the current is leading the value of voltage, or the current is lagging voltage or leading the value of voltage. And after that, we need to take the representation of both the voltages VR and VL with respect to a resultant voltage vector. With respect to an resultant voltage vector. So how to draw the phasor diagram? First, we need to take the current as reference. Why? What is the reason why I am taking current as reference? As it is a series circuit, the current flowing in the first element in a series circuit is equal to the current flowing in the last element. Current flowing in the last element. Then after, depending upon the properties of the elements that are connected in the circuit. So what are the elements that are connected in the circuit? The first one is resistor and the second one is inductor. So the property of resistor is current will be always in phase. Current will be always in phase with the value of a voltage. Current will be always in phase with the value of voltage. What is the current? Current is nothing but it is indicated by I in the given circuit, and the voltage across the resistor is what? VR. So in case of a resistor, according to its property, current will be always in phase with the value of the voltage. In phase with the value of voltage. So this is the current that is flowing into the circuit. We have taken it as a reference, and the voltage across the resistor is always in phase with the value of what? In phase with the value of the current. That is one of the important property of a resistor. Now coming to the next element, inductor. So what is the property of an inductor? Current will always lag the value of voltage by how many degrees? 90 degrees. Lagging is nothing but what? Being in the backside. So this is the current reference I have taken. Current should lag the value of voltage by how many degrees? 90 degrees, and this is the property of an inductor. Now I have taken the representation of VR and also the representation of VL by taking the representation vector as a current. By taking the reference as a current, by considering the properties of a resistor, and also by considering the property of an inductor in phase with the value of voltage and current is lagging the value of voltage, I have drawn the representations for VR and VL. So the resultant of the VR and VL can be drawn like this, where this is indicated as V equal to VR plus VL, or else it can also be represented as I into J. Or else it can also be represented by I into Z. So as I have followed this step by step, this complete representation which is trying to you to analyze the behavior of the elements that are connected in the circuit, this representation is called as a phasor diagram. This representation is considered as what? It is considered as a phasor diagram representation. What is the first step? You need to take the reference vector. What is the second step? You need to consider the properties of the different elements that are connected in the series, that are connected in the circuit. Either they may be connected in series, there may be two elements, there may be three elements, or they may be connected in parallel. What is the procedure you need to follow? First, you need to take the reference position. Next, you need, by considering the properties of the passive element that are connected in the circuit, depending upon those properties, you need to draw the vector representations of the resistor or inductor or capacitor that is present in the circuit. Then you need to draw the resultant. So this final representation, what we have got in the form of this particular graph, is considered as a phasor diagram approach. So this is the phasor diagram representation of a series RL circuit. Now I want to derive the expression for the impedance that has been observed in a series circuit. Impedance that is observed in the series circuit. For that, I am trying to apply the KVL in the given. So what is the circuit we have considered? A series RL circuit where an AC voltage is given VR and VL. So by applying KVL in this particular loop, sum of the voltages applied equal to sum of the drops across the elements. Sum of the drops across the voltage drop across the element, that is V equal to VR plus VL. How I got this expression? By using what? By using KVL. By using KVL in the above circuit, voltage applied equal to voltage drop, sum of the voltage drop across the each element. What is the number of elements that are connected in the circuit? Two elements, those are R and L. voltage drop across the resistor is considered as VR, and voltage drop across the inductor is considered as VL. So by applying a KVL in that particular loop, the expression what I have got is what? V equal to VR plus VL. As we know that the voltage across the resistor from the Ohm's law is considered as what? V equal to I into R, and the voltage across the inductor is considered as I into XL. Just substitute these two parameters in the given expression. By substituting, whatever I will get is V equal to IR plus I into XL. By taking I as common, R plus XL. R plus XL. So V by I equal to R plus JXL, Z equal to R plus JXL. This is how I am trying to calculate the value of impedance from the given expression. If I want to calculate the value of magnitude, Z equal to under root of R square plus XL square. I into JXL. VR will be equal to I into R. VL will be equal to I into JXL. So by considering this particular expression, I am getting the value of impedance as Z equal to V by A equal to R plus J into XL. R plus J into XL. This is how you need to calculate the value of a impedance for all the series type of circuits. We need to calculate the value of impedance. For the parallel circuits, you need to calculate the value of admittance. For the parallel circuits, you need to calculate the value of an admittance. So from this circuit, I am getting the expression as V equal to I into R plus JXL. V by I equal to what? R plus JXL. So according to the definition of an impedance, V by I can be considered as what? Z. So Z equal to R plus JXL. If I want to calculate the value of magnitude of impedance, it can be considered as R square plus XL square. R square plus XL square, where Z is considered as the total impedance offered by the circuit. Where Z is considered as the total impedance offered by the circuit, and the units for impedance is considered as ohms. So by using the expression for the impedance, whatever I have got by applying the KVL in the closure path. So what is the expression I have got for the impedance by applying the KVL in the closure path of the circuit? Z equal to R plus J into XL. If I want to represent the same thing in the form of a diagram, it can be represented like this. So this is nothing but R, and this is nothing but what? XL, and this is the resultant of both R plus JXL, which is represented as Z. So this is called as what? This is called as impedance triangle. This is called as what? Impedance triangle, where it is trying to represent the value of resistance and also the reactance of a circuit. Where it is trying to represent the resistance and also the reactance of the circuit. This triangle obtained by using the expression of what? Z equal to R plus J into XL. Z equal to R plus J into XL, where Z is the total impedance offered by the circuit. Total impedance offered by the circuit. Now coming to the next thing, phase angle calculation. Phase angle calculation. So in series RL circuit, we know that the current lags the value of voltage by 90 degrees. Current lags the value of voltage by 90 degrees. So that 90 degrees is considered as what? Is considered as by phase angle. Is considered as phase angle, and it is generally represented by the expression tan phi. And it is generally represented by the expression tan phi. Now by using the phasor diagram representation, whatever you have got I, VR, and this is nothing but what? VL, and this is nothing but what? V. By using this particular representation, I can, by using this particular thing, what is the value of tan phi? Tan phi is nothing but what? Opposite side by adjacent side, that is VL by VR. Where tan phi is used to represent the phase angle of the given circuit. Phase angle of the given circuit. So from the phasor diagram, the expression for the phase angle, that is tan phi, can be considered as tan phi equal to VL by VR. And we know the value of VL, where it is represented by VL equal to I into JXL, and you know the value of VR, I into R, by using the value of Ohm's law. Just substitute all those parameters, and we are trying to get the value of tan phi, phase angle, for a series RL circuit as XL by R and the phase angle phi can be considered as tan inverse of x by r. This phi is considered as the phase angle. In order to calculate the phase angle, you need to calculate the value of tan phi, and this tan phi is calculated from what? From the phasor diagram. This tan phi is calculated from what? It is calculated from the phasor diagram. After calculating the value of tan phi, in order to calculate the phase angle, I am using this particular expression, phi equal to tan inverse of XL by R. Here XL is the inductive reactance, where XL is the inductive reactance offered by the circuit, and R is the resistance offered by the circuit. And R is the resistance offered by the circuit. So in order to calculate the phase angle, I am trying to analyze the value of a tan phi by using the phasor diagram representation. How was my phasor diagram? This was my phasor diagram where I have taken the current as reference, and by using the properties of resistance, I know that current will be in phase with the value of voltage, and by using the property of inductor, I know that current will lag the value of voltage by 90 degrees, and this is the resultant, which is equal to V, and I can take this particular VL opposite side as this one phi. So by using tan phi from this particular circuit, I can make that opposite side by adjacent side, VL by VR. So by considering the phasor diagram in action, I am trying to calculate the value of tan phi. After calculating the value of tan phi, in order to calculate the phase angle offered by the series RL circuit is considered as phi equal to tan inverse of XL by R. Now coming to the next definition, that is power factor. So in general, the power factor is taken as a ratio of real power to the apparent power, or else in case of our thing, power factor is generally represented by a term cos phi. So by applying the cos phi again in case of a phasor diagram, cos phi is nothing but what? Opposite side by hypotenuse. By applying the cos phi in our phasor diagram, what is our phasor diagram? Current, and current in phase with the value of voltage with respect to the property of a resistor. Current lags the value of voltage by 90 degrees, and this is my resultant V. Again, I am considering this particular thing. So cos phi is considered what? Opposite side, VR by hypotenuse V. So cos phi is the power factor of the given series RL circuit, and which is given as VR by V. I know the value of VR, I into R, and I know the value of supply voltage given as I into Z. So cos phi for the series RL circuit is represented as R by Z, where R is the resistance offered by the circuit and Z is the impedance offered by the circuit. So in general, the power factor is defined as the ratio of real power to the apparent power, and in general it is represented by a term cos phi. And in our series RL circuit, we are trying to calculate the value of power factor by using what? Again, by using the phasor diagram representation. By using phasor diagram representation, I am trying to calculate the value of cos phi. In general, according to our trigonometric terms, we are calculating the value of cos phi by using the formula of adjacent side by hypotenuse. So adjacent side in case of our particular phasor diagram, what we have considered is considered as VR, and the value of hypotenuse is considered as V. And the value of hypotenuse is considered as what? V. So we know that the value of VR in general is represented from Ohm's law as I into R, and the expression for the voltage given in the form of a supply is given as I into Z. So by substituting these two parameters in the expression of power factor, that is cos phi, I am getting the value of cos phi as R by Z. So what is our final conclusion here? The cos phi, the power factor of the series RL circuit is given as R by Z. Here I am representing a power triangle, where the power triangle is used to represent the different types of power that are present in a circuit. You can see here active power on one side, reactive power on other side, and one more side it is considered as a total power or apparent power. We know the general formula for complex power is indicated by S equal to P plus JQ, where S is represented as apparent power or total power, P is represented as real power or true power or active power, and Q is represented as a reactive power, and Q is represented as a reactor. We are trying to represent all those powers in a simple triangle nomination, and hence it is considered as a power triangle. And hence it is considered as a power triangle, where S is represents the total power of a circuit or apparent power of a circuit in terms of VA. The units for the total power is considered as VA, and active power, reactive power in terms of active power in terms of watts, kilowatts or megawatts, and reactive power is measured in terms of volt ampere reactive, that is VAR. VAR. As these three types of powers are represented in the form of a triangle, I am showing you the representation as power triangle approach. Power triangle approach. So this is how you need to calculate the different, analyze the behavior of a series RL circuit, and we are trying to calculate the value of a steady state response. Steady state response. So what is the procedure? First, you need to draw the circuit diagram with respect to the combination given to us. Then you need to draw the phasor diagram. Then you need to calculate the impedance if it is a series circuit. Then you need to calculate the phase angle. Then you need to calculate the value of power factor. Finally, the power triangle. The power triangle. So we will meet in the next combination, and we will try to analyze the behavior and also calculate the steady state response of the other combinational circuit. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.